Pattern recognition is nearly synonymous with machine learning. This branch of artificial intelligence focuses on the recognition of patterns and regularities in data. In many cases, these patterns are learned from labeled training data, but when no labeled data are available, other algorithms can be used to discover previously unknown patterns. The terms pattern recognition, machine learning, data mining and knowledge discovery in databases are hard to separate, as they largely overlap in their scope. Machine learning is the common term for supervised learning methods and originates from artificial intelligence, whereas KDD and data mining have a larger focus on unsupervised methods and stronger connection to business use. Pattern recognition has its origins in engineering, and the term is popular in the context of computer vision. A leading computer vision conference is named Conference on Computer Vision and Pattern Recognition. In pattern recognition, there may be a higher interest to formalize, explain and visualize the pattern. Whereas machine learning traditionally focuses on maximizing the recognition rates. Yet, all of these domains have evolved substantially from their roots in artificial intelligence, engineering and statistics, and have become increasingly similar by integrating developments and ideas from each other. In machine learning, pattern recognition is the assignment of a label to a given input value. In statistics, discriminant analysis was introduced for this same purpose in 1936. An example of pattern recognition is classification, which attempts to assign each input value to one of a given set of classes. However, pattern recognition is a more general problem that encompasses other types of output as well. Other examples are regression, which assigns a real-valued output to each input. Sequence labeling, which assigns a class to each member of a sequence of values. And parsing, which assigns a parse tree to an input sentence, describing the syntactic structure of the sentence. Pattern recognition algorithms generally aim to provide a reasonable answer for all possible inputs and to perform most likely matching of the inputs, taking into account their statistical variation. This is opposed to pattern matching algorithms, which look for exact matches in the input with pre-existing patterns. A common example of a pattern matching algorithm is regular expression matching, which looks for patterns of a given sort in textual data and is included in the search capabilities of many text editors and word processors. In contrast to pattern recognition, pattern matching is generally not considered a type of machine learning, although pattern matching algorithms can sometimes succeed in providing similar quality output to the sort provided by pattern recognition algorithms. Pattern recognition is studied in many fields, including psychology, psychiatry, ethology, cognitive science, traffic flow and computer science. Overview: pattern recognition is generally categorized according to the type of learning procedure used to generate the output value. Supervised learning assumes that a set of training data has been provided, consisting of a set of instances that have been properly labeled by hand with the correct output. A learning procedure then generates a model that attempts to meet two sometimes conflicting objectives: perform as well as possible on the training data, and generalize as well as possible to new data. Unsupervised learning, on the other hand, assumes training data that has not been hand-labeled, and attempts to find inherent patterns in the data that can then be used to determine the correct output value for new data instances. A combination of the two that has recently been explored is semi-supervised learning, which uses a combination of labeled and unlabeled data. Note that in cases of unsupervised learning, there may be no training data at all to speak of. In other words, the data to be labeled is the training data. Note that sometimes different terms are used to describe the corresponding supervised and unsupervised learning procedures for the same type of output. For example, the unsupervised equivalent of classification is normally known as clustering, based on the common perception of the task as involving no training data to speak of, and of grouping the input data into clusters based on some inherent similarity measure, rather than assigning each input instance into one of a set of predefined classes. Note also that in some fields, the terminology is different. For example, in community ecology, the term classification is used to refer to what is commonly known as clustering. The piece of input data for which an output value is generated is formally termed an instance. the instance is formally described by a vector of features, which together constitute a description of all known characteristics of the instance. Typically, features are either categorical, ordinal, integer-valued or real-valued. Often, categorical and ordinal data are grouped together. Likewise for integer-valued and real-valued data. Furthermore, many algorithms work only in terms of categorical data and require that real-valued or integer-valued data be discretized into groups. Probabilistic classifiers. Many common pattern recognition algorithms are probabilistic in nature, in that they use statistical inference to find the best label for a given instance. Unlike other algorithms, which simply output a best label, often probabilistic algorithms also output a probability of the instance being described by the given label. In addition, many probabilistic algorithms output a list of the n best labels with associated probabilities, for some value of n, instead of simply a single best label. When the number of possible labels is fairly small, n may be set so that the probability of all possible labels is output. Probabilistic algorithms have many advantages over non-probabilistic algorithms. They output a confidence value associated with their choice. Correspondingly, they can abstain when the confidence of choosing any particular outputs is too low. Because of the probabilities output, probabilistic pattern recognition algorithms can be more effectively incorporated into larger machine learning tasks, in a way that partially or completely avoids the problem of error propagation. How many feature variables are important? Feature selection algorithms attempt to directly prune out redundant or irrelevant features. A general introduction to feature selection which summarizes approaches and challenges has been given. The complexity of feature selection is, because of its non-monotonous character, an optimization problem where given a total of features the power set consisting of all subsets of features need to be explored. The branch and bound algorithm does reduce this complexity but is intractable for medium to large values of the number of available features. For a large-scale comparison of feature selection algorithms see. Techniques to transform the raw feature vectors are sometimes used prior to application of the pattern matching algorithm. For example, feature extraction algorithms attempt to reduce a large dimensionality feature vector into a smaller dimensionality vector that is easier to work with and encodes less redundancy, using mathematical techniques such as principal components analysis. The distinction between feature selection and feature extraction is that the resulting features after feature extraction has taken place are of a different sort than the original features and may not easily be interpretable, while the features left after feature selection are simply a subset of the original features. Problem statement. Formally, the problem of supervised pattern recognition can be stated as follows: given an unknown function that maps input instances to output labels, along with training data assumed to represent accurate examples of the mapping, produce a function that approximates as closely as possible the correct mapping. In order for this to be a well-defined problem, approximates as closely as possible needs to be defined rigorously. In decision theory, this is defined by specifying a loss function that assigns a specific value to loss resulting from producing an incorrect label. The goal then is to minimize the expected loss, with the expectation taken over the probability distribution of. In practice, neither the distribution of nor the ground truth function are known exactly, but can be computed only empirically by collecting a large number of samples of and hand-labeling them using the correct value of. The particular loss function depends on the type of label being predicted. For example, in the case of classification, the simple 0-1 loss function is often sufficient. This corresponds simply to assigning a loss of 1 to any incorrect labeling and implies that the optimal classifier minimizes the error rate on independent test data. The goal of the learning procedure is then to minimize the error rate on a typical test set. For a probabilistic pattern recognizer, the problem is instead to estimate the probability of each possible output label given a particular input instance, that is, to estimate a function of the form where the feature vector input is, and the function f is typically parameterized by some parameters. In a discriminative approach to the problem, f is estimated directly. In a generative approach, however, The inverse probability is instead estimated and combined with a prior probability using Bayes' rule, as follows. When the labels are continuously distributed, the denominator involves integration rather than summation. The value of is typically learned using maximum a posteriori estimation. This finds the best value that simultaneously meets two conflicting objects, to perform as well as possible on the training data and to find the simplest possible model. Essentially, this combines maximum likelihood estimation with a regularization procedure that favors simpler models over more complex models. In a Bayesian context, the regularization procedure can be viewed as placing a prior probability on different values of. Mathematically, where is the value used for in the subsequent evaluation procedure, and the posterior probability of, is given by. In the Bayesian approach to this problem, instead of choosing a single parameter vector, the probability of a given label for a new instance is computed by integrating over all possible values of, weighted according to the posterior probability. Frequentist or Bayesian approach to pattern recognition. The first pattern classifier the linear discriminant presented by Fisher was developed in the frequentist tradition. The frequentist approach entails that the model parameters are considered unknown, but objective. The parameters are then computed from the collected data. For the linear discriminant, these parameters are precisely the mean vectors and the covariance matrix. Also, the probability of each class is estimated from the collected dataset. Note that the usage of a Bayes rule unregistered trademark in a pattern classifier does not make the classification approach Bayesian. Bayesian statistics has its origin in Greek philosophy, where a distinction was already made between the a priori unregistered trademark and the a posteriori unregistered trademark knowledge. Later Kant defined his distinction between what is a priori known before observation and the empirical knowledge gained from observations. In a Bayesian pattern classifier, the class probabilities can be chosen by the user, which are then a priori. Moreover, experience quantified as a priori parameter values can be weighted with empirical observations using, for example, the beta and Dirichlet distributions. The Bayesian approach facilitates a seamless intermixing between expert knowledge in the form of subjective probabilities and objective observations. Probabilistic pattern classifiers can be used according to a frequentist or a Bayesian approach. Uses. Within medical science, pattern recognition is the basis for computer-aided diagnosis systems. CAD describes a procedure that supports the doctor's interpretations and findings. Other typical applications of pattern recognition techniques are automatic speech recognition, classification of text into several categories, the automatic recognition of handwritten postal codes on postal envelopes, automatic recognition of images of human faces, or handwriting image extraction from medical forms. The last two examples form the subtopic image analysis of pattern recognition that deals with digital images as input to pattern recognition systems. Optical character recognition is a classic example of the application of a pattern classifier, COCR example. The method of signing one's name was captured with stylus and overlay starting in 1990. The strokes, speed, relative min, relative max, acceleration and pressure is used to uniquely identify and confirm identity. Banks were first offered this technology, but were content to collect from the FDIC for any bank fraud and did not want to inconvenience customers. Artificial neural networks and deep learning have many real-world applications in image processing. A few examples: identification and authentication, for example, license plate recognition, fingerprint analysis and face detection verification. Medical diagnosis, for example, screening for cervical cancer or breast tumors. Defense, various navigation and guidance systems, target recognition systems, shape recognition technology, etc. For a discussion of the aforementioned applications of neural networks in image processing, see for example, in psychology, pattern recognition. Making sense of and identifying the objects we see is closely related to perception, which explains how the sensory inputs we receive are made meaningful. Pattern recognition can be thought of in two different ways, the first being template matching and the second being feature detection. A template is a pattern used to produce items of the same proportions. The template matching hypothesis suggests that incoming stimuli are compared with templates in the long-term memory. If there is a match, the stimulus is identified. Feature detection models, such as the Pandemonium system for classifying letters, suggest that the stimuli are broken down into their component parts for identification. For example, a capital E has 3 horizontal lines and 1 vertical line. Algorithms for pattern recognition depend on the type of label output, on whether learning is supervised or unsupervised, and on whether the algorithm is statistical or non-statistical in nature. Statistical algorithms can further be categorized as generative or discriminative. Classification algorithms. Parametric, linear discriminant analysis, quadratic discriminant analysis, maximum entropy classifier. Note that logistic regression is an algorithm for classification, despite its name. Non-parametric, decision trees, decision lists, kernel estimation and k-nearest neighbor algorithms, naive Bayes classifier, neural networks, perceptrons, support vector machines, gene expression programming, clustering algorithms. Categorical mixture models, deep learning methods, hierarchical clustering, k-means clustering, correlation clustering, kernel principal component analysis, ensemble learning algorithms. Boosting, bootstrap aggregating, ensemble averaging, mixture of experts, hierarchical mixture of experts, general algorithms for predicting arbitrarily structured labels, Bayesian networks, Markov random fields, multilinear subspace learning algorithms, unsupervised, multilinear principal component analysis, real-valued sequence labeling algorithms. Supervised, Kalman filters, particle filters, regression algorithms. Supervised, Gaussian process regression, linear regression and extensions, neural networks and deep learning methods. Unsupervised, independent component analysis, principal components analysis, sequence labeling algorithms. Supervised, conditional random fields, hidden Markov models, maximum entropy Markov models, recurrent neural networks, unsupervised, hidden Markov models. See also. References. This article is based on material taken from the free online Dictionary of Computing prior to November 1, 2008 and incorporated under the relicensing terms of the GFDL, version 1.3 or later. Further reading, Fukunaga, Kinosuke. Introduction to Statistical Pattern Recognition. Boston, Academic Press. ISBN A0-12-269851-7 Koutroumbas, Konstantinos. Theodoridis, Sergios. Pattern Recognition. Boston, Academic Press. ISBN A1-59749-272-8 Hornegger, Joachim. Paulus, Dietrich W. A Applied Pattern Recognition, A Practical Introduction to Image and Speech Processing in C++. San Francisco, Morgan Kaufman Publishers. ISBN A3-528-15558-2. Skorman, Jürgen. Pattern Classification, A Unified View of Statistical and Neural Approaches. New York, Wiley. ISBN A0-471-13534-8. Godfrey T. Toussaint, ed. Computational Morphology. Amsterdam, North Holland Publishing Company. Kulikowski, Casimir A. Weiss, Shalom M. Computer Systems that Learn, Classification and Prediction Methods from Statistics, Neural Nets, Machine Learning, and Expert Systems. Machine Learning. San Francisco, Morgan Kaufman Publishers. ISBN A1-55860-065-5. Jane, Anil K. Duin, Robert P. W. Mao, Jian Kang. Statistical Pattern Recognition, A Review. IEEE Transactions on Pattern Analysis and Machine Intelligence 22, 4 €37 doi, 10.1109/34.8248119 An introductory tutorial to classifiers, external links, the International Association for Pattern Recognition, list of pattern recognition websites, Journal of Pattern Recognition Research, Pattern Recognition Info, Pattern Recognition, International Journal of Pattern Recognition and Artificial Intelligence, International Journal of Applied Pattern Recognition, Open Pattern Recognition Project, intended to be an open-source platform for sharing algorithms of pattern recognition, OpenNN, Open Neural Networks Library.